Okay, I'm going to talk about a revolution in Bayes factors, a re-volution in psychology. And it was actually this word, John Krushka's used the term re-volution once in his blog post, and I think he's also used it in a paper. I thought it was appropriate here because I'm going to revisit an old area, an old topic in psychology, namely hypothesis testing and parameter estimation. Now the thing is, if we're going to use the term revolution, what we need in the first place is a revolution. So you might think to yourself, okay, what is actually going on in psychology? I missed a slide. The Bayes factor. There we go. I guess everyone knows what it is. It's likelihood ratio evidence is given the hypothesis. There we go. There it is. It provides a continuous index of the strength of evidence provided by the data. I guess everyone's familiar with that, and I nearly jumped over this slide. Yes, what's actually going on in psychology? Well, I went to a popular database of abstracts in psychology, namely PsycInfo. I use this quite a lot. And I typed in the word Bayes factor. And I just searched for it in the text of abstracts. It could be keywords and so forth and so forth. And, well, you can see that there's certainly something going on. In 2000, we've got a line down here, and it increases and it goes up year on year. I don't know what happened in 2016. There wasn't so many papers published with the term Bayes factor in the text. And, well, you think, crikey, perhaps something is going on. But then when you look at this a little bit more carefully, and actually I'm going to focus on last year, 2017, you might notice that in actual fact there was just 104 papers published, or 104 records in PsycInfo with the term Bayes factor in the text. So this isn't really a revolution. In fact, we might think of this as a rather small student party. And anyway, I went through and I looked at some of these papers, and to characterize this a little bit, we've got some hardcore partygoers here, and they're writing sort of theoretical articles, tutorial articles. We got a very good paper by Rasmus actually that year with Bayes factor in it. Well worth a read, very good paper. Some very good papers, some very good theoretical tutorial papers, and we've also got some empirical papers. These are people who've actually set out with a meaningful problem, and what they want to do, what they do is they motivate their problem. They motivate it well in their introduction, and then they're going to go out and collect some data and actually use some sort of method to analyse their data to draw some conclusions on the basis of their data. And these are the papers, this is the work I'm going to focus on, and it's from, as I say, 2017. So the first thing you might ask is, well, what sort of reasons are people giving for why they're using Bayes factors? Well, of course, in some papers, there's absolutely no reason given at all. Well, hey, who needs what reason? In others, these are some of I took these quotes from some papers. One we've got here, p-values are notoriously hard to interpret. Well, we know that there's lots of papers about the misinterpretation of p-values and so forth and so forth. So we might go along with that one. We've got another one here, a good alternative when having to work with small samples. I guess that's good if you've got informed priors, not so good otherwise. I didn't look that closely at this paper. By far the most common reason given is to obtain odds for or against the null hypothesis, to help interpret main results that did not reach an alpha of 0.05, or, this one I particularly like, because our primary findings were not statistically significant. So this is there we go, you've formulated your fantastic empirical collection. You've gone out, probably spent several weeks, if not months, collecting your data. You don't get statistically significant results. What a bummer. So what they do then is compute a Bayes factor, or they compute some Bayes factors. So the typical format of the papers that I've seen in 2007, this is empirical papers, lovely introduction, meaningful question, collect some data, analyse your data using traditional frequentist methods, then go, I haven't got statistically significant results, but I want to get published anyway, therefore I'll compute some Bayes factors. So that's the format we've got. And then what do people conclude on the basis of their analysis? Well, sadly, most of these people are using this to test the null hypothesis and tend to come to the conclusion that the null hypothesis is true. And of course, we're well aware that no single study is really going to shed that much light on the truth or falsehood of any hypothesis. But this is the typical conclusion that people come to. And this actually even makes it into the title of the paper, some of these papers. So we've got no effect of X on Y, no relationship between this and that in this, and so forth and so forth. Fortunately, I'm glad to say there's not many, but there are a couple of examples that are there of this. The other thing you find in these papers is that sampling variability is often ignored or underestimated. Well, this is not surprising. You're not going to write up your fantastic study and say, well, actually, I can't really say much on the basis of this study because, well, I simply got sampling variability. I simply didn't test enough people. In other words, I've got low power. You're not going to point this out. You're never going to get published. You've got your number of participants there. You can let the reader decide for themselves. You certainly don't want to point it out in the paper. So I would say, in short, and I think this is fair enough, certainly students and researchers, we conduct experiments because we want to know about the truth or falsehood of our hypothesis. And this is typically the conclusions that are being drawn in these papers. And they're using Bayes factors then to say, okay, well, the null hypothesis is true or false. So if people are using the null hypothesis, they've got their standard classical frequentist analysis. They don't get statistically significant results. They find there's lots of free software now available, some very good software that enables the easy calculation of Bayes factors. There's some online calculators, you've got JASP, you've got R packages, and so forth and so forth. It makes you start wondering, okay, what's the relationship between p-values and Bayes factors? And some of you might already know this, but I did some simulations. Okay, what have we got here? Well, each plot's based on 1,000 simulations, and I drew my samples from these are just 2 independent samples, following a normal distribution. You can see here that I've plotted my Bayes factor on the y-axis, and I've actually, in this case, I inverted it, so larger values support the null hypothesis. I did that simply so this line would go upwards that way. And I've plotted my p-values on the x-axis. Well, I think you can see the relationship is very, very close, if not 1-to-1. Now, bearing in mind that these were simulations, these numbers are approximate. These weren't exact calculations, but look at this. This is effectively the power of my test. This is p is less than 0.05. Here I've defined an effect size of 0.3. So if you want the alternative hypothesis is true, I get a p-value less than 0.05, and I get that 44% of the time. Let's have a look at my Bayes factor, and actually I should have said that I computed these Bayes factors using the default priors as defined by Murray and Rauder in their Bayes factor package. This, of course, would depend on your sample size, effect size, and priors. But look at this. I've got 0.441, 0.45. And as you increase sample size, you might expect this to go up. Here I've got 55%, 54%. And do bear in mind, these are simulations, so they're never going to be exact. Here I've got 63%, 61%. So as my sample size increases, the sensitivity, the power of my study increases. But we can see there's a very, very close relationship between p-values and Bayes factors. And I use the default priors here, the default prior specifications defined by Murray and Rauder, because actually, if you look at the papers in 2017, what they've typically done, they've conducted their main analysis using standard software such as SPSS. They've then computed their Bayes factors, and they've simply gone for the default priors. So I thought that seemed a very reasonable thing to do. Okay, so given this close relationship between p-values and Bayes factors, I started to think about Geoff Patching. Now, I expect you all remember Geoff Patching. If you don't, I keep jumping slides. This is just the case when the null is true. When the null is true, you can see here, now we've got p is less than 0.05, we've got a 5% error rate. Here, well, it's 0.06, we've got 6% error rate. It remains relatively constant regardless of sample size. So my error rate's about the same. Here we go, I've got 5%, 0.42%, and so forth and so forth. So that's simply the case when the null hypothesis is true. Now, as I said, given that we've got such a close relationship between p-values and Bayes factors, it brings to mind Geoff Patching. And if you haven't seen this video clip, it's well worth watching. He'll appear in a minute. I just want to do this. He'll come on in a minute. There we go. There he is. Fine fellow. I won't play it. I guess, has everyone seen this? Okay, some people have, some people haven't. If you haven't seen it, it's well worth watching. One of the things that Geoff Patching does in this clip, it's called Dance of the P-Values, is, well, we get a table, and what he does, oops, I've gone a bit too far. He gives our p-values, I'm not sure you can see this that well, he gives our p-values some sort of characteristics, what it's like, what does it feel like for a researcher to get different p-values. So here we've got, and actually we might actually want to redo this table. Now here we've got non-significant, here we've got no effect, effect is here we've got despair, depression, and here we've got medication, reconsider life. We might say here, do Bayes factor analysis. So we can change these around a bit. If we've got approach and significant, we've got counselling. So he characterised p-values in this way. Well, I guess for those of you who've been working in Bayesian things, you're probably aware that we have labels as well, characterisations of the Bayes factor. It started off with Harold Jeffreys. It's recently been amended. The most recent characterisation is we've got 1 to 3, a Bayes factor of 1 to 3. That's anecdotal. We've got 3 to 10. That's moderate evidence. We've got 10 to 20, strong evidence, and so forth and so forth. And I just this starts to become dangerous, because as soon as we've got labels on things, this implicitly implies some sort of cut-off. So, hey, my BF has gone above 3. Dancing. And I've got a quote here by Rich Moran. I particularly like this. He said, "Here we see the major problem. The use of these labels smuggles arbitrary meaning into the judgment where none is needed." Well, he's definitely right. None is needed, but well, hey, I thought I'd smuggle some arbitrary meaning into the Bayes factor. So here we go. I got this from, of course, Geoff Patching. I followed his approach. So here we go. We've got Bayes factor between 1 and 3. Frustration, if only. Oh, it's anecdotal evidence. Actually, Jeffreys said it was not worth a mention. And that's been recently changed. Here we've got 3 to 10. Okay, this is moderate evidence. Consolation prize, fair publication. You never know, we might get something out of it. Here we've got Bayes factor greater than 10. We've got great pleasure, dancing, drinking. Well, for those of you who are familiar with dance of the p-values, the other thing that Geoff Patching did, he had some little figures to characterise what it feels like when you get different. But and guess what? I got some little figures. So here we go. Here I'm assuming that in actual fact, the person who set this up, they're hoping to support the null hypothesis. So here we go. I've got a BF less than 1 over 10, 2 stars, jump for joy. I've got a BF between 1 over 10 and 1 over 3, happiness. Here, of course, if we get a BF going the other way, that's supporting our alternative hypothesis. I've got annoyance, surprise. Here I've got depression. And for those of you who are into stick values, into stick figures, you can get really carried away with this, which I did. So here's some R code. And, okay, we're just It's always a bit nervous. Oh, there we go. Again, if you've seen, I'll just move that in the middle. So what have we got here? I'm doing all right for time. I've got two distributions. The blue distribution has got a mean of 0 and a standard deviation of 1. I've got a red distribution. This has a standard deviation of 1. I've set the mean at 0.3. So in Cohen's terms, I've got a small to medium effect size. I'm going to draw 75 points from each distribution. Obviously, the little blue dots come from the blue distribution. Little red dots come from the red distribution. And these little dots here, this is just the mean of my sample from the red distribution. And this is my mean of my sample from the blue distribution. So let's see if we can get this little stick figure to dance. Yay! Here we go. Dancing stick figure. And you can see there's a lot of dancing going on here. We've got stars, we've got arms going everywhere. It's, there we go, it's great, isn't it? And, of course, this is just a graph. That was just 100 simulations. But this, again, is our relationship between our base factors. And, again, this is, I computed the base factors just using the default prior distributions defined by Murray and Rouders and Jamil, and my p-values here. How does this stack up? I've got 100 simulations here. How does this actually stack up if I do a few more? Oh, incidentally, if you're really into stick figures, I won't put it on, but there's a characterization of p-values also on XKCD. And we're doing for time. Okay, we keep going. Can I keep going a little bit? This is how they stack up. We've got a small to medium effect size. We've got 75 participants in each group. That's quite large. It's very laborious and timely to run participants. You can see we've got base factors just about everywhere. We've got 56% in favour of the null hypothesis. In this case, the effect size was 0.3. We've got 21, 33, 46% in favour of our alternative hypothesis. This pretty much matches the power of our study. So they're going all over the place. What happens when the null hypothesis is true? Well, we've got about 5%, like you'd expect. Well, this is all very good. And if you're familiar with Geoff Cummings' work, you'll know that he already goes on to talk about parameter estimation. So this is a independent t-test. I took this from John Kruschke's paper. If you're really interested in this, I recommend you read the paper. It's very good. He models these as t-distribution. I'm primarily interested here in the estimation of effect size. Of course, we get estimation of all our parameters from this. The mean, the highest, 95% highest density interval. And there we go. I really did get carried away. Just see, this is a bit slow because I'm using JAGs. Am I all right? You went over a bit, didn't you? So okay, what have we got here? We've got our blue distribution, mean 0, standard deviation 1. Green distribution, we've got 0.3 mean. We've got a little stick woman this time. A little stick figure for the BF, and you can see this is our estimate. This is our mean effect size, and this is our 95% highest density interval. Okay, well I'll leave that on. What I'm going to do is, if you're familiar with Geoff Cummings, you probably know exactly the conclusion that I'm going to come to, that parameter estimation is a lot better than Bayes factors. So I'll just jump over the next two slides and put on the take-home message. Well, the take-home message here is, if you do a frequentist analysis and you follow that up by doing Bayes factors, I can pull out all the sad old mems that I used to use when teaching about Bayes factors, p-values, and in actual fact I can very easily change them to Bayes factors. We've seen that the interpretation of the Bayes factors is dependent on the sensitivity of the design. Bayes factors alone indicate nothing about the magnitude of the effect or the precision of the estimation. For that we need parameter estimation. Parameter estimation is more informative. We get full estimates on all our parameters, we get our confidence intervals, highest density intervals and so forth. And I will say that although this is more taxing for students, we really should focus on parameter estimation in our teaching. Oh, I thought I had 20 minutes, and then Rasmus told me I had 18. Would you? Yeah, absolutely.